Cross-country plans. Hi. We've got a great one today. We're here for about 45 minutes. We're talking to Honza, who is a meteorologist. He's a 5 times X-Alps pilot. I'm feeling a little bit nervous, actually, because, you know, it's about meteorology, it's about weather. I feel like I'm going for a test. To ease us in, we've got Martin, Honza's son. Now, Martin and Honza have done pretty cool things. Vol bivouac in the Alps. That's them on the left. Hi, Martin. How you doing?
Hi.
Cool. You see that picture there on the screen? That's you and your dad, I think, last year. Where was that?
That was in the Alps. I think that was on our second day.
It was in Chamonix.
Oh, okay. Yeah, that was more on our 5th day flying over Chamonix.
Okay.
That day started off when, so we were at this one spot, then we hiked up about 300 meters vertically, and we launched, and that was the one time where I gave my dad advice that he didn't listen to.
Okay.
And it made us sink out. Because we were flying along this mountain ridge, and it was going straight and then turning right. And my dad decided to go diagonally through it and not go along the mountain ridge.
Okay.
And I was like, why don't we go along there? The one thing that I've learned from flying with you is that it's better, the thermals are better up on the mountain ridges instead of in the valley.
Okay.
So we sunk out in Chamonix, then we hiked up about 1,000 meters and got this one really nice late, 6, 7 o'clock flight. And then we landed somewhere and set up camp.
That is awesome. How old are you, Martin?
I'm 11.
11. And how old were you when you first flew with your dad?
What was it?
When you first flew? I think you were 1 or 2.
Yeah.
2 years old.
Yeah, 1 or 2.
And what do you like about it?
The flying, first of all, seeing the sights from up there, it's a whole different perspective.
Okay.
And it's really fun, just the thought of we need to get thermal so we can go up, and then we need to fly along this way, and I just really like it.
Cool. And what's the best thing you've ever done on a paraglider with your dad?
The best thing, that's hard, but I've got to go with our second sky camp trip, where we had this really nice 5.5-hour flight, and we got that day to our goal, and the year before we tried the same goal, and we had 6 days to do it, and we got about halfway there in those 6 days, but that time, in 4 days, we were at our goal.
That's brilliant.
The weather was really nice. And yeah, so that I really liked that flight. It was so much fun just being able to fly into the Dolomites, into Colorado, which was our goal.
Beautiful. And is there anything about it you don't like?
About flying?
About the sky camping trips?
I really enjoy it. I'm not sure there are many downs. Maybe one of the disappointing moments is where we get to a patch where we think there will be blueberries, but somebody has already picked out all of them.
Okay, yes. About the food. I'm with you on that one. Okay, cool. So on a scale of 1 to 10, how cool is your dad?
9.
So there's work to be done. All right, cool. And what's your favorite cloud?
Favorite cloud?
Mm-hmm.
I've got to go with the cumulus. The small ones that are just starting to form, because those, what I've noticed so far, have the best thermals.
They have the best thermals. Cool. We're going to talk about the development of cumulus clouds in a little bit. Honza, I've got a few quick-fire questions for you as well as a warm-up.
Okay.
You did the X-Alps 5 times.
Yes.
And what was your best result?
The best was on my second attempt in 2009, and through, I think fortune and other people's misfortune, I managed to get onto the podium and stand next to Hoffer and Maurer. So that was really cool.
That's cool. Can you come a little bit further closer to the mic?
Yeah.
Yeah, that's better. That's much better. Okay, and so that was the best year for you. What's your best memory from the X-Alps?
Well, the best memory? Gosh, there are so many. But I think in some ways that, there were some really nice long flights, and those are very memorable. But the day in 2009, when I did make the podium, it was the second to last day, because we had Aiden Toast and Evgeny from Russia. We were all in the Chamonix area and very, very close, basically within 5 kilometers of each other starting that day. And Evgeny was a big runner, kind of like Toma Kokonea, maybe not quite as good, but very, very much a runner. And Evgeny's obviously a very good pilot. So, I figured I somehow had to outsmart these guys, which was not easy. And the day started off with a low base, and we had to, there's a lot of little hopper flights, side hill landings, hiking up a little bit. And this was before really great navigation. I mean, I had a little Garmin E-Trex GPS and fold out map. So sometimes I would land and try to even figure out where I was. And through a combination of about 9 flights, including a long flight after I got past the area of Bourg Saint-Maurice and got over Col d'Isère. I think it's Col d'Isère, or maybe, past Col d'Isère, Col d'Isère. And, I was able to get far enough ahead of Aiden, and then Evgeny had sunk out in a stable layer earlier. So it was putting it all together. It was really putting all the pieces together and making it work. And then back then we could do all night, so just hiking through the night to get as far as possible. Yeah.
Cool. And what's your favorite cloud?
I would have definitely have to say cumulus as well. Yes.
And how long?
Well, Martin's probably going to have to get back to. He's got a class.
Okay.
Do you have any more questions for Martin?
No, this is mine. Thank you very much. I think that was cool.
Okay.
And hey, you're going sky camping again, aren't you, in September in this year, hopefully?
If it works out with Corona, then yeah.
Okay, cool. All right. Well, keep in touch.
Locally.
Thank you very much for your time.
Bye.
Have a good day. Bye. Bye. Super cool kids, Honza.
Thanks.
So yeah, when did you start flying?
I started back in. Well, I first tried it in '92. I was 17. I was at a camp in Quebec to learn French, and these guys were. It was Canada Day, which is like their Independence Day, and they were in the park kiting their paragliders. They would plan to do a paramotoring show, but it was too windy. And I got talking to these guys, and I was able to do a few lessons with them. And I really wanted to get my gear right there. I thought, okay, this is my one chance to fly. I'm 17 years old. I got to do it now. But I didn't have the money, and wrote a letter to my folks, and they kind of did their research and got me in touch with the local club, and finally figured out it was best to wait a little bit and save up my money and learn locally. So in '93, so long story short, spring of '93, I started flying here in California. And
what glide did you fly today?
Excuse me?
What glide did you fly? What wing do you fly?
Oh, it's the Trango XC3. It's the same one I've been on the same wing for 5 years now, which kind of either speaks to how old the wing is or how little flying I'm doing. I think I'm probably in the 60 to 100 hours a year range right now, just busy with the kids and work. So yeah, the same one I flew in the 2000. It was crispy new for the 2015 X-Alps, and it's definitely nearing the I would say, the end of its life, but it still goes well.
And what's your favorite place to fly?
Oh gosh, there are so many places. I mean, of course, the Alps as a regional place is probably the highest on the list. But then there's some really, I mean, I love flying we have a little cabin down in Chile. I've had it been going down there since '04, and even though it's not super flying friendly, it's really nice because you're exploring, you're figuring out your local convergence areas, you're figuring everything out. There's no other pilots really flying distance there. So when it works, it's magical to fly over these araucaria forests and fly with the Andean condors. So yeah, I would say it's hard. It's so hard to pin down one favorite place. I mean,
Fine.
I was blown away by in Maui on the lee side, Lahaina. It was just a magical place to fly. So it's really hard to pin it down to one favorite spot.
Cool. Okay, right. For people who are watching, we're going to take it a little bit slowly through this session, because what we want to look at is thermal development, and we're going to look at some weather forecasting and different clips, and we have some slides. Actually, we're going to look through some slides. Hopefully someone is going to post a link in the comments on Facebook where you can download these slides so you can look at them before or after, or view it if you're here. Okay, so I'm going to hide this slide of you guys and bring in the first slide. So Hans, are you ready to talk about this one? This is about the stagnation zone.
Yeah. So what?
Let me ask you first. Why did you want to talk about this specific thing?
I think this is something that took me a long time to figure out, that the way we see the terrain is not the way the air sees it necessarily. Like, to best this on this slide, what we see is you can be on the upwind side of something, and the air can be relatively calm, almost deceivingly calm. So I've always advocated for having knowledge of what the wind is doing at the top of a mountain. That's really important. If there's an anemometer, if there's any way to have that knowledge, that's important. If you're unable to get to the top of the mountain that you're planning to fly, or if you just have no information what the wind is doing up there, and you just want to be careful that even on the upwind side of the mountain, you can be in a place where the air is very calm while it's still very strong on the periphery. So, the stagnation zone, a great illustration of the stagnation zone is the leading edge of a paraglider. We see the open cells on the paraglider. The wind sees a closed leading edge because the air is rammed into the paraglider, and the pressure kind of it equalizes the back pressure, the little local high equalizes against the wind coming at it, so it acts as a solid surface. So what the wind does when it encounters terrain, it inserts these stagnation zones. It also, in certain places, it'll insert almost like roller bearings, which to us feel like shear and turbulence. But kind of the long story short of this is, if you can't go to the top of the mountain, you might want to check the periphery. You want to check the side of the mountain. Mm-hmm. There was a great example of this with I think it was it was in the last X-Alps, I believe, and we were near the Zugspitze, and Tom called me. Tom Dodorlote called me, and he said, "Are you even thinking of launching? It's just blown like stink right here." And they were a little bit, maybe 2 kilometers away, if that, maybe 1 kilometer away, and on the side of the mountain. And I was a little more on what was the upwind side, and I had nothing to even pull up a glider in.
Wow.
So it's,
So you were right in the stagnation zone.
I was in the stagnation zone, yeah.
From the ground,
even on this
could you tell that there
Yeah,
was?
even on this volcano picture, you can hike. This inspired an article I wrote a long time ago. But I remember being on the volcano. It was blown like stink at the top, probably 40 miles an hour, 60 kilometers an hour. Very strong on the sides as we hiked up, because we came up the side that we're looking at it, and then I hiked down the upwind side about 300 meters below the crest. Is 0 to 5 knots. I mean, it's very, very light and still. You'd have to wait for a cycle to pull up in. But if you were to launch in that, you would very soon fly up into, fly into the strong wind that is still present. So it's something just to be aware of and not to be lulled by an upwind stagnation zone.
Okay, cool. The next slide.
Yeah, the next 3 slides, just I can preface it, basically go into, just like I was saying, the air doesn't see the terrain the way we do. Numerical weather models don't see it the same way either, and that's for a different reason, but it's kind of a resolution thing. It's they see it very smoothed out. This might be, we might see valleys and ridges, and they just see smooth like undulations. Even, for example, for global models, you get the ECMWF global model is a 9-kilometer grid scale, and you need 4 grid boxes to start to resolve something.
When you talk about grid scale, explain that.
Think of it as pixel size. I think the best way is think of it like a pixel size. And if you want to see something, how many pixels do you need to make sense of what you're seeing? So if you're zooming, if you're trying to see the Alps, imagine seeing the Alps, and 9 kilometers by 9 kilometers is your finest resolution pixel. So a lot of things won't even show up in there. Then that's a global model. Then you have some regional models that get much tighter on that with smaller. Go ahead.
Let's go back. So when we're talking about model, we're talking about weather models. So
yes.
Who actually creates the weather models that we look at?
Okay, so it's a long iterative process, and some very, very smart people work on it. And many are kind of research models, and then if for the forecasting models, as new data gets assimilated in, there's a lot of research done also to figure out if it improves the forecasts or not. So if a new satellite goes up, assimilating that data, So I'll back up one more step. When a model runs, it basically takes, let's say, a forecast of 6 hours into the future, and then as that time arrives, a bunch of data comes in, and that data has to be blended into that forecast from 6 hours ago, and then that's the new starting point. That's the best understanding of the state of the atmosphere at the time, and then it can time step forward from there on. And that's basically just solving a bunch of numerical equations, and that gets complicated. But the it depends. It takes in balloon data, it takes in aircraft data, it takes in surface station data, a lot of satellite data. All this stuff is basically telling you the state of the atmosphere, what it's now, and then the performance of the model is different models, use slightly different schemes to run forward with that information.
And we're trying to build a picture of what the weather is going to do over the next 6, 12, 24, 36 hours. That's what these weather models are trying to do, right?
Exactly. That's what they're doing.
I mean, it just took me forever to understand this, which is why I'm really breaking it down. Is the resolution of most of these models is 9 kilometers less. It's about that, right?
Yeah. For example, this is the global models. There's 2 main global models: the ECMWF and then the GFS. So the European model and the US model. And then there's regional models, a bunch of different regional models that can take that kind of the boundaries, those coarse boundaries, and then run it on a higher resolution over a local area. So then you can start to resolve some of the bigger, wider valleys in the Alps, and you get better resolution, but still it's dependent on what's coming into the model. Like it's from the global model. The global model is trying to encompass what's happening on the whole Earth, and then the regional models are basically an insert of that. So think of like a blurry picture, and then inside of that you have a region that's higher resolution.
Okay.
But what comes in, if that's not good quality, you'll get higher resolution looking weather, but it might not be the correct weather.
Okay. I mean, this is all a way of explaining why, as pilots, we need to be weather forecasters, because we operate on a much smaller scale than 9 kilometers, right? So
absolutely, and that's why a lot of what we fly around in is the fancy way of saying is subgrid scale processes are happening, but that's things that are happening at a scale that is much smaller than what is being resolved by the model. And how a lot of that behaves isn't absolutely well known. It's not, they do some experimental runs, and we'll see one of those from the LES in a moment, large eddy simulation. But, understanding, for example, how a thermal behaves or how thermals behave in wind is extremely complex. I mean, think of, if you're making some porridge and it's boiling, think of how that behaves, and if you move the pot a little bit to the side of the stove and how that changes the dynamics of it. Also, then if you start stirring it, how does that affect the boiling? I mean, the stirring is kind of the wind. So, a lot of what we fly around in is a boiling river of air in complex terrain, and it's infinitely hard to.
It's infinitely hard to predict. Let's look at this this video. I'll drop these out. It's a 45-second clip. I think
just preface the video. So what you're seeing here, what you'll see when Ed plays it, this is it's modeled. It's squished a little bit in the horizontal, so the thermals would be a little bit wider. It's about 30 kilometers wide, 2 kilometers tall, so it is squished. But what you'll see, the red is the kind of the stable layer. You can kind of think the inversion at the top of the thermals. The blue would be the thermals going up, and then what goes up must come down. And then you'll see it'll, the boundary layer, the layer with the thermals, does get taller over time as it goes through the loop. But you also watch individual thermals and watch regions where air is sinking as well and suppressing some of the smaller thermals. So I'll let it play. Yeah, so it's on a loop. So you'll see it'll restart right now. So you can see top of lift is less, and then as the thermals grow, they mix in some of that stable air from above. You'll also see regions where thermals prefer to go up, but for everything that goes up, it must come down. And really, we can only use the strongest parts of the thermals. The thermals are much wider than what we can use. So we're basically using the cores of the thermals. Of course, on glide, if somebody's able to on transition be in parts, take advantage of parts of thermals that might not necessarily be going up as quick as your sync, great, but they can extend your glide. But you can see how also small thermals or even pronounced thermals can be sort of squashed by returning flow.
Yeah,
that's a great little video to loop and play.
We have that video. We put it on our YouTube site actually, so people can go there and have a look at it.
Cool. And then just to give credit, that was created by a guy named Ned Patton from the National Center for Atmospheric Research. That was about 14 years ago. He sent me that video, but it's been very useful. I've always found it really fun to look at. How
much research is there into that sort of thermal activity? I can't imagine it. I mean, it's sort of
there is some, what it is a lot of this research. They try to understand these smaller scale processes, and then the net sum of that is basically going to be used in some of the larger models. So if for example, this mixing, they're not going to resolve every thermal, but they know, okay, this rate of heating over this kind of surface is causing mixing, or heats the lower atmosphere at this rate. That can be used for larger models later, or some of the stuff can be used for very specific modeling, like this large eddy simulation is what they call this. but they, for example, if they're putting in new buildings somewhere and they want to know how that's going to affect the flow somewhere, if they're planning on putting in some skyscrapers, they can use some of this to model how that skyscraper is going to affect the flow in the city if they need that
Okay.
on a specific scale.
So I think that's given us a good idea of what's going on in the air that we're flying in as cross-country pilots. Here's a slide. Your next slide is what thermals look like. Do you want to talk us through this one?
Yeah, this one, basically it's kind of a stop motion, a little bit of what we saw. It's now it's the scale is a 1-to-1 height, in height and in the horizontal. But what you see is, as we saw there, it's got similar color coding where it was the blues were the parts going up, and then you can also see the upper level outflow and kind of lower level inflow. I spaced on the name, but the fellow who wrote the book on thermal flying, he talks about these the winds, like the thermal portion, the portion of the wind that you feel that's related to the thermal. Like when you can sometimes be topping out, and if you imagine if all this is in a wind, you might be on the outflow part and suddenly feel like the wind's really picked up because you're kind of. Excuse me.
Burkhard Martins was his name.
Burkhard Martins, yes, correct. Sorry, I forgot his name. So he talks about this, and this kind of, I feel this illustrates it fairly well. Also, you also see the descending air coming down in there from above. But yeah, you kind of yeah, this is another good one. Kind of shows it in a different color scheme, but it shows a little cloud, and it shows just there's the idea, the core is the most protected. On the periphery, you get a lot of mixing, which slows it down. A thermal is born at the surface, and the air gets extra warm. That's where it gains its buoyancy. It's a little layer called the superadiabatic layer. It's in the first maybe few tens of meters. The air gets extra warm, maybe gains about a degree or two, maybe 3 degrees Celsius. Warmer than the surroundings. That's where it gains its buoyancy, coalesces, starts to rise, and then much of the air on the sides gets mixed out very quickly. That also increases the volume of the thermal, but it's not that much warmer than the surroundings anymore. It's as long as it's a little warmer than the surroundings, it accelerates upward. Then it goes through a layer where it's no longer accelerating necessarily, but it's ascending, mixing a little bit on the sides, and then it gets to the stable layer, and that's where you see that real kind of that mushroom top. And this shows you how you can have people if you're topped out in a thermal, you can be kind of bouncing around near the top and have people catch up to you from below. You can be doing your best at core, but if you're at the very top, you're kind of just hanging out, and people can catch up through the core and catch up to you.
That's a really great question. How do you, obviously if you've got a cumulus cloud above you, like that's the top of the thermal, but if you haven't got a cloud above you, and for me, it's always just a feeling. It's like, oh, I've reached the top of the thermal. How do you tell you're at the top of the thermal?
I think it's a little tough to know whether you're at the top or whether you've lost it. It's always but as you can see, some of these, and as we saw in the video, it's a very dynamic thing. So some of even the stronger parts can kind of peter out, especially if they weren't very wide. If they lose a lot on the sides and mix a lot of the peripheral air, and they quickly lose their buoyancy. Skinnier than tall thermals will often, they might have a lot of initial punch to them, but they mix out, and then you lose it. Sometimes you have a great thermal, and there's just descending air from above that just squishes it right down. So I think to me, to this day, it's hard to say whether I'm at the very top or whether I've just lost it, whether I need to. It's tough because do you increase your circle diameter and expand your search pattern to look for a better core, or do you are you truly at the top of that thermal and kind of hanging out to see take it as high as it will go? So it kind of depends on where you are and if you need more height or what your predicament is.
When you're flying, you have a lot of weather knowledge. When you're flying, do you think about meteorology all the time?
I think it's better, but I'm not necessarily, it's having a mental model, and I don't think for this you necessarily have to have a degree in atmospheric science or anything like this. If you're, it's good to know what things to check prior to going flying, but once you're flying, you've got a model of how the air behaves, and ever since you start flying, you start out with a basic model, and each time you go flying, you refine that model. Each time you fly in a different place, different country, different location, you get to launch. I always recommend, take 10 to 15 minutes to observe what's going on before you launch, even before you get your kit out, unless it's, obvious that it's, everybody's flying and it's perfect. It's really good to take, things happen in these 15 to 20 minute turnaround cycles. So if there's going to be a really strong gust, it'll probably come around, within that 15 to 20 minute cycle, you should get the peak gust. So these things, you want to observe things from the ground, and over time you will, you'll get a sense of what's going to be going on in the air just by everything you've observed from the ground. Now, of course, even to this day, I occasionally get surprised. I thought kind of, okay, this is how it's going to be, and then you get a little surprise, and then but you want to reflect on that too. Like, what, it didn't just come out of nowhere. Like, what was that? Why was it a little windier there? Why was there not wind there when I thought there would be wind, and things like this. So it's.
Do you find it easy? Is it easier for you to sort of do the flying weather in the flatlands or the mountains?
And I've flown a lot more in the mountains than I've flown in the flats. I've had a few nice flights in the sort of the big flat Central Valley of California, but my flatland flying is very limited. I would say I'm much more of a mountain pilot.
Cool.
So
listen, I want to skip ahead into what we want to talk about, which is the transition from good flying day into a sort of crazy day. So I'm going to skip the couple of slides on soundings and things like that.
Yeah, soundings that's a whole. I would highly recommend learning to read soundings. It would take a long time to explain it properly, and there's some great tutorials on that. But I keep the one thing I've got on my phone is I check. I'll check my sounding, and I'll check a few wind reports from that are near my flying sites in the mornings, and then I'll see the kind of day I'm missing.
Okay. So listen, why do you want to talk about this? The transition from shallow to deep convection. What is that?
So shallow convection is what we like. Shallow convection is basically thermals in what we in the boundary there. Thermals with nice, sometimes blue sky thermals, sometimes thermals topped with nice fair weather cumulus. Often those cumulus that are fair weather cumulus will be just the top of the thermal is formed cloud, but it's still already in a kind of a negatively buoyant phase. It's dying out. It's kind of what we saw in that animation of thermals, where they're just topping out and then sloshing back down. Now, deep convection is basically convection of the whole troposphere. So the troposphere is, say, on average about 10 to 12 kilometers, shallower in the polar regions, up to 16, 17 kilometers in the tropics. But boundary layer convection, what we like, that's the boiling within the convection within the boundary layer. When you get the whole troposphere starting to boil, we're talking cumulonimbus. We're talking, that video, that one shows it well. You don't want to be in that. That is just, and what's happening there, the explosive growth of that is you can have a really deep layer above the boundary layer where, from kind of where the cloud starts to form to the top of the troposphere, where the air, temperature is still dropping off with height, but as water condenses and releases a lot of what's called latent heat of vaporization, a lot of the energy it took to evaporate water, as as the little droplets are forming in the cloud, that's releasing heat. And yes, air rising in that cloud is still cooling with height, but not as fast as it would as if it were just a thermal. A thermal, it's going to be basically 1 degree C per 100 meters. That's a given. How quickly air will cool within a rising cloud depends on how humid that air is, what the dew point was, at the base of the cloud. The more humid it is, the slower the air will cool as that cloud rises, and you can have this really deep layer where now the cloud, as it's formed, starts to become positively buoyant and becomes ever more positively buoyant, meaning it can accelerate ever faster. And
so
you can
how high do the cu-nims go to?
So they'll go, and now once again that depends and where in the world you are, but it would be
In the Alps.
somewhere from as little as 8 kilometers to up as high as maybe 16 kilometers in the tropics. The tropical ones go really, really deep. The ones we'll see over Europe and over the US are, I'd say topping out often in the 12-kilometer range. Now, of course, their tops will overshoot a little bit too. They'll
Okay.
you get all this vertical speed. I mean, you get incredible upward speeds. That doesn't just stop when you reach neutral buoyancy. Now you have to negatively buoyant. What puts the brakes on it eventually is the fact it becomes the very top becomes negatively buoyant, and you'll see a little bit of that sloshing. Even in that picture, it kind of overshoots a little bit and sloshes, and you'll see that a lot of time lapse of clouds. You'll see a really good looking cloud grows strong, and then it kind of dries out quick. Because it's overshot, become negatively buoyant. Now it starts sloshing back down. Anytime air starts sinking, it's drying. Plus, it's been mixing on the periphery, so it dries out.
So, what sort of climb rate can you get in a cloud like that?
Oh, it can get like 20 meters per second or more, and some really, the extreme ones that you hear of in the Midwest that create baseball size or grapefruit size hailstones. Basically, those hailstones fall and they get caught up in it and recycled several times and coated. And to suspend something the size of a baseball or a grapefruit, there you've got to have probably 50 meter per second winds going straight up.
What 50 meters a second? So what are the dangers of flying near cu-nims?
Well, you can become kind of confetti to a vacuum cleaner, really. I mean, there's a point where, short of cutting away and free falling out, having that glider overhead in any stalled or tangled configuration, it's still probably going to go up and create a real big hailstone out of you.
Looking at this this time lapse here, there are actually quite a lot of nice little clouds around it. So that's obviously the whole system. Can you tell me a little bit about how much influence the cloud has, the storm cell has? How wide does it go? I remember flying in Australia, and they were always over there, sort of 40 kilometers away, and you'd see them building. You're never quite sure how close you can get to them.
Yeah, that's a tough one. A lot of that has to do, has to do with your terrain. Like if you're out in complete flats, even though the cumulus cloud that we're watching there is, it's encompassing several cubic kilometers. I mean, if it's growing, let's say 8 kilometers tall, it could be as much as 8 kilometers wide. I mean, that's a lot of cubic kilometers of air. That's got to come in from somewhere. So on the surface, there's going to be a lot of converging winds under that. As that all goes up, a lot, that air is coming in from somewhere. So at the surface, there's going to be a lot of surface convergence. What, out in the flats, there's, probably 10, 15 kilometers away from that, you can still be safely flying, but you really got to be careful of what's going on with your other clouds overhead, because I guess another way of putting it is a lot depends on what the wind is doing aloft. If there's a steering wind and it's bringing it towards you, or if you're on the crosswind or upwind side of these things, it's something that definitely not to be flirting with too much. But like you said, 40 kilometers away, I think if you're safe. If the sky overhead of you overhead of where you are is fine, and you see a cu-nim 40 kilometers away, it's good to know that the sky has the potential to blow up, but it could be something over that region that is accentuating it and helping it blow up there and where you're at. So it's not a cu-nim 40 kilometers away to me is not an immediate sign of I have to land now. In the mountains, it gets to be different because that cu-nim went to, if it will probably drop out, it'll rain, you can have a massive gust front, and then in a sense that's like an avalanche that's burst. And when you have valley systems, the cold outflow is, it's a density current, so it behaves almost, it runs where water would run, like a big burst dam. And in those cases, you got to be really careful if you start seeing any kind of rain shafts. Even 20 kilometers away or more, a valley can channel that gust. That gust front can be channeled down a valley and can be very, very vicious at the bottom of the valley. And I've always said, if you've gotten yourself in a predicament where things are blowing up really big, and you maybe made some bad choices and you stayed in the air a little too long, you might want to think of, if you're in a mountainous area, land up high. If there's a high meadow up high, you could be on the ground up high 10 minutes sooner than you would be if you're trying to get to the valley floor. If there was a gust front, you could end up having to deal with that gust front in the valley, where it's less likely the gust front's going to affect areas near the mountaintops rather than down low. So even a high snowfield might be the place to land and wait it out. And then have
you ever been gust fronted by a storm cloud?
I unfortunately have not been I've been very close to where I'm packing up, and it starts raining and gets really windy. So that I've been close to where I should have been on the ground sooner. It was almost like a squall line. I remember it was in Annecy, and it was marching in from Grenoble, and the whole thing was moving at about 30 kilometers an hour as a line of thunderstorms. So it was overcast, kind of decided to sled her out, and then there was a little light lift. I was playing around in it, and suddenly two valleys were starting to show rain shafts, and there I should have probably landed up high in retrospect, but I went and spiraled down to the valley, and by the time I packed up, it was windy and raining, and it had arrived. So I felt I got lucky on that one. It was a little kind of lucky and stupid kind of feeling.
Hey, we have a question on the comments from Ariane Tudor. Do you know Ariane Tudor? Can you comment on your OTB flight in Boulder? What's OTB?
Oh, over the back, maybe over the back. Oh yeah.
What were you looking for, weather and wind wise?
So in Boulder, what I was looking for is light westerlies, because you're flying on the east side of the Rocky Mountains, so you don't want to have strong westerlies mix down and flush down into your flying area. So it was, I checked the sounding. There's very light westerlies all the way up to, I think, 6,000 meters, and there were two very memorable flights I had. It was back in 2007, just as I was training for the X-Alps, for my first X-Alps. And I got to fly and basically there's low-level easterlies. It's converging on the Continental Divide, which was maybe 25 kilometers away. So I rode the low-level easterlies, thermals in those easterlies towards the divide, got up to well over 5,000 meters at the divide, and caught the light westerlies, and was able to fly most of the way back in the westerlies before dropping back into the easterlies and getting back to Boulder. And it was it was a beautiful flight. I've even got a track log. I don't have it here in the PowerPoint, but it was one of the earlier issues where I was writing articles, but it shows, you could see the thermals tracking westward with the easterly winds, and then it feels the westerly winds, and then it tracks back. So the track log is a little bit of a zig and a zag as it transitions from an east wind to a west wind.
Cool. Listen, I just want to go back to this one briefly. Can you just talk us through what's happening here? This is a classic flying day. This is a time lapse of about an hour and a half in South Africa. And this is what we're looking for, basically. Can you just using your meteorologist's eyes and your pilot's eyes, tell us what you're seeing in this clip. I'll drop out so we can play it bigger.
Yeah, so this day looks like I got pretty fair weather cumulus. I see what seems like a fairly deep convective layer. It's hard to tell. You got no mountains, so it's hard to judge exactly how high cloud base is. But the fact that the clouds are pretty wide as they form is telling me that the boundary layer is pretty deep. Thermals are pretty far apart, but then they're strong. The one forming over the tree right now is growing a little taller, but still I see nothing to worry about as far as overdevelopment at the moment. The one over the tree that's coming over the tree is showing a little more vertical development. We're looking kind of upwind, mostly upwind. The clouds are coming towards us. I see also wind on the ground, just but the way the time lapse is you see the shaking of the trees and the bushes. The one forming over the tree right now is starting to show a little more vertical extent, and that would, I would keep an eye on that one. So I think it went away now.
Sorry, I lost control of the deck there for a second. Okay, thanks. Listen, I wanted to show one other. Thank you for that, Honza. I wanted to look at one other video clip, and I chose this because it's a sort of 30-second clip, I think, and it shows the cloud. What looks like a nice cloud, but I'll just play it and then we can see what happens. So if I'm on glide to that now, I'm getting really disappointed.
Yeah, that one petered out. You didn't quite make it to it. And I've had experiences like this where I've gone for a perfect looking cumulus cloud, left my thermal, went full speed bar to get to it and got there and it was nothing but sink, because that one, looks like it overshot its top, got negatively buoyant, started to dry out. You can see it dries out fairly quickly and it kind of disappears. And then what we don't see is the air sloshes back down underneath it. It's kind of going back to that LES modeled animation of thermals. What goes up must come down, and then some of those sloshes go all the way to the ground. And this reminds me of a cloud in Peru a long time ago, flying to the cloud and then being in sync all the way down to the deck and landing and seeing a sky full of perfect cumulus clouds. The most annoying thing is when on a perfect a sky full of good-looking cumulus clouds, you chose to dive for one, it died on you, and then
so as it's dying, it's not the top that's dying, the whole column is dying.
Yeah. I think if we go, do you still have that animation? This would be a great time if we can go back to that Ned Patton animation.
Let me find that.
Because if we play that again, I think that'll bring a lot of this home again. Is how, things, they're buoyant, they go up, then they overshoot on momentum, but become negatively buoyant, and then slosh back down. And if you watch some of the air that comes, you can see the air that's come from quite a ways down because it's drier, it's more red or yellow. But you'll see some of the ones that shoot up really strong kind of come sloshing. There's a sloshing effect, and some of that sloshing effect, if you think about it, on a paraglider, we're very slow to get out of that sink, so we could be in bad sink all the way to the ground. And I've had that a few times. Just been scratching my head. How did I sink out on such a good day? But you can see, if there's great strong lift going up, there's unless you've got a source, something that's really feeding a cloud constantly, and you can kind of separate the area where it's going to slosh back down, or if there's a little bit of wind, sometimes you'll have a little bit of wind that helps kind of take the negatively buoyant part downwind, and you can keep forming good cloud on the upwind side. But if it's in a relatively light wind scenario or out over the flats, as this would be, it just yeah, what goes up must come down, and we can only take advantage of a very small part of what's truly going up, because that's the core, that's the part that's going to overcome our sink rate. So we have to be really smart about it to stay up, even on a good looking day.
Sophie Tudor has asked a question. When we are under an active dark cloud, a potential cu-nim, i.e. we can't see in profile, so we're below a cloud, it's dark, and we don't know what's up there, we don't know how high it is. How can we understand if it's a cu-nim or just another good cloud to extend an XC flight?
Well, it's a tough one, because the darkness, a lot of that sometimes depends on if there are other clouds above. Sometimes there can be some cloud. So let's pretend it's a fair weather cumulus day. There's no high cirrus clouds, nothing else making it darker than the cloud itself. I'd still be very, very careful on a cloud that's getting really dark. And if you're working your way up to base, be at the edge of it. Don't center underneath a really dark cloud like that. I would say be on the very periphery of it, because that means if it's fairly dark, it's gonna have some depth to it. And
why is it dark?
Why is it dark? Just because it's deep. It's blocking the sun's rays. It's a deep cloud. If a thin cumulus cloud is not going to be very dark. So dark usually means it's got a lot of vertical extent overhead, and in that case, it's probably not just a forced cumulus cloud that's kind of topped out on momentum. It's actually going to accelerate upward, and in those kinds of clouds, you might get not all cumulus clouds have cloud suck. A lot of those fair weather ones that just kind of top out and are the top of a thermal, and that's it. They're forming the cloud adds a little bit of buoyancy, but it might not be enough to overcome the fact that they're already negatively buoyant and wanting to slosh back down eventually. A big cloud like that, though, might start to sort of tap into what we call this latent heat of vaporization. It might, have the tendency to want to accelerate upwards and regain strength. And you want to. That's where we hear of cloud suck, and that's when you want to, at best, approach it from the very edge and be ready to speed bar away, or leave it be if it's too dark. And a lot of this has to do with visibility. If you're in a very humid, dirty air place, it gets much harder to judge these things. If you're out in like in Australia, or out in Owens Valley or the Sierras or the Rocky Mountains, most of the time the air is fairly clean. There's not big pollution sources. It's very dry, and then you have much better perspective of these things. But there's many days in the Alps where visibility was maybe 20 kilometers at best, and then some of these things it's much harder to judge these things and judge the distances and judge the extent of these things when you have poor visibility.
Yeah. Okay, cool. Thank you. Listen, we're on sort of 55 minutes, so got a few minutes left. Hello, Didier Hero from La Réunion. Have you flown in La Réunion?
No, I passed through there when I was 15 through the airport, but I would love to fly Réunion sometime. Yeah, I guess it seems like it's the Hawaii for the French.
Yeah, it looks nice. You get croissants and everything. It's cool.
Yes.
Listen, let's just finish off by thinking about how to make a pilot forecast, because we started off with some quite technical stuff about 9-kilometer resolution models and all that. And we understand that we have to know about clouds, we have to know about weather for our scale, what's happening on our mountain in our valley. So can you give us some advice on how to make a pilot forecast? When do you start? Yeah. If you're looking to fly on Saturday, for example, when do you start looking at the forecast?
I mean, you can start looking as far as 5 days out. 3 days, you start to get a little more, more reliability to it. What's really nice, I've been using that Windy app is really good, because Windy actually they purchased the ECMWF data. The GFS data is publicly available. ECMWF is like $250,000 a year, so they've purchased that data, and made it available to pilots and kite surfers and everybody, which is amazing. It was programmed by the guy who's he's like the Larry Page of the Czech Republic. He started Seznam, which is a search engine, but he's got the capital and he's a kite surfer. So he wanted to make this available to the public. And then I think they've done some fundraising. But Windy is really good because you can check different forecasts. You can check, both of the global forecast and depending which region in the world you're in, you can check some regional forecasts if they exist for that region. Not every place in the world has a regional forecast, so you might just be stuck with the global forecast. But even that, comparing the two, is really nice. You can work your way up through the levels. So I'm often, if I'm looking to fly the Sierras, which is a 2-hour drive, before even thinking whether something might be good on the weekend, I'll kind of look at the wind at the 3,000 meter level, that's the 700 millibar level, and basically look at what my wind's going to be doing. Because if it's going to be too windy, I mean, you can have great thermals, but you just don't want to fly really, really strong wind. It's just not that fun. So wind is my first thing. Just, is it going to be blown out or not? That's my foremost. Then for overdevelopment, I might check the CAPE values. CAPE is convective available potential energy, but it's a short little, you can get a numerical value, and values over 500 for a lot of places mean there's a good chance it's going to blow up to thunderstorm. If there's a regional weather forecasting office, it's worth reading their discussion. Different places in the world, have different levels of discussion. Some don't have it, but if they have it, you got to realize it's not geared towards pilots. It's geared towards the general public. They maybe have a short aviation section, short maybe fire weather. All these things are good. And then if it's a flying site that you fly often, having bookmarked anemometers that are relevant to your flying sites, certain mountains that have wind reports, and lastly, soundings. If you can learn to read soundings, and if there's a sounding that goes up, they're about 150 kilometers apart. They're pretty far apart because they're expensive to launch and involve somebody going out twice a day with launching a weather balloon with a piece of equipment that is basically lost eventually.
I've got to show these guys the picture of you with the balloon. This is what we didn't do, soundings. We didn't take a quick look at soundings, but here you are. And you just what you're doing.
A research project in Owens Valley, but it's just showing how big. Yeah, it's about a 1 meter balloon, and before it burst, it's about the size of a house, and it burst at about 30 kilometers of altitude. But it goes up. It's got a little GPS on it, a little radio to send all that information back, and it can measure temperature and relative humidity. And since it's a balloon, the ground speed of the GPS is the wind speed, at that elevation. So the nice thing about a sounding, you get this it's a cluttered looking plot, but once you learn to read it, you have wind, temperature, and dew point temperature. So you can quickly tell, okay, this looks like you start to see what looks like the fingerprint of a good day. And that, to me, looking at one of these, I can quickly see like, oh, okay, this temperature's dropping off quickly with height for a great distance in altitude. It could be a good day. So yeah, a lot of these things have to kind of come together. But for me, checking the soundings, if I'm looking way out, I want to know about the wind. Also, just checking cloud cover. I mean, it could look like the wind's good, everything's good, but there could be high clouds that come in and shade everything over. So
cool. All right. So advice, if anyone is still in lockdown, I know that lots of people still are in lockdown, go online, find out how to read a sounding. There's a whole
there's a good site. I want to kind of pitch a site. It's called, if you Google MET-Ed and UCAR, M-E-T like meteorology, ed like ed, and UCAR, U-C-A-R. You should, there's all these modules that are free. You just have to, you sign up, but there's no fee. They just want to know who you are, but that's fine. And there's hundreds of modules for, for people interested in weather. One of them is called SKU-T Mastery, because these are called SKU-T log P diagrams, these soundings.
Okay.
So they kind of lead. They kind of, you can work through that and learn to read the sounding. But they've got all sorts of things like gap winds and mountain meteorology. There's all sorts of things. So if you're in lockdown looking for some weather things to brush up on weather, there's great modules in there.
And all for free. All right. Well, listen, Honza, thank you very much for your time.
Yeah, thanks, Ed.
And great to meet Martin and have him online. He's pretty cool. And I know that you're hoping to head off to Switzerland later this year to do another trip.
We'll see. Yeah, it's I think I got a 5-10% glimmer of hope. I'm holding open that it. We got flights, I think mid June that we bought well before this coronavirus thing started. So we'll have to play it by ear. We'll see where things stand at that time, mid June, as far as even making a trip over. But if not, we'll do it next year.
Excellent. All right. Well, listen, thank you very much for your time.
Thank
I
you.
know lots of people have enjoyed this. It's one for the weather geeks. We all love looking at the clouds, and
All right.
hope to be back out there again soon. Excellent.
Yeah.
Switch off. Thank you, guys. Thanks for
Okay.
watching, everyone. Bye-bye.